Hello, my chemistry faithful. Unit 9, video lecture 4, redox half reactions. There are 3 of these, I believe. When you are done with today's video, so this is the real deal Holyfield, you will be able to say, I can determine how oxidation numbers change during a single replacement reaction. You will also be able to say, I can identify and write oxidation and reduction half reactions to show movement of electrons. You will also be able to say, I can identify oxidizing and reducing agents, the opposite, within reactions. Let's get right to it. This is the meat and potatoes of the whole unit. Ready? Identifying oxidation and reduction reactions. Well, first we got to find the metal that's being swapped out. So in this particular case, the Mg and the Ca are the ones that are swapping. And you can see that Ca is a lone element on the reactant side, so that's for sure. And then the metal in the compound, where these are always going to be not double replacement reactions. They're going to be single replacement reactions. So there's going to be a lone metal and then a metal in a compound. Pull them out. These are the 2 metals that are swapping. Then track the changes in their oxidation states. So Mg is going from a +2 to a 0. Okay. And Ca is going from a 0 to a +2. Okay, good. Then we have to write out these half reactions together. So Mg +2 goes to Mg0. So +2 means more protons, right? And so he must have lost electrons, so he's gaining electrons to get to 0. So which side do I put gaining electrons on? Gaining electrons goes on the reactant side. Bam. See how we work that out? Then the other half reaction is Ca0 to Ca +2. Well, there's how many electrons are being changed? 2, 0 to 2, right? So that's a given. So it's 2, just is it on the reactant side or the product side? So I go 0, whole same number of protons and electrons, to +2. Protons is winning by 2. If protons are winning, what happened to I must have lost electrons. So if I lose electrons, just like when I lose heat, that goes on the product side. Bam. These are the 2 half reactions without those big spaces. Those are the teaching spaces. So it would, that you can move that CaO in, you can, there won't be any space left after the MgO. Okay, but we will put the zeros in, or, they are kind of insinuated, but I say we put them in so we really see what's going on. Okay. Overall, redox half reaction shows both half reactions with equal number of electrons on both sides. So here we come to the final balancing of real equations. And then we actually have to balance those electrical charges. The reduction half reaction must show just the element that's being reduced. Both forms of the metal are shown, reactant and product, and the number of electrons gained on the reactant side for reduction. Okay? Okay, good. Whew. And then the oxidation half reaction shows just the element that's being oxidized. Both forms of this metal are shown, reactant and product, with the number of electrons being lost on the product side. Oxidation is losing product side, just like losing heat. Okay, now here we go. These are the opposites, oxidizing agents. So the element that is being reduced is the oxidizing agent. They're responsible for the gaining of electrons lost by the elements being oxidized. Oxidation is losing. So if in order for an element to oxidize and lose its electron, there must be somebody around to grab it. Okay? So he's the agent. He's the partner in crime, if you will. To give them credit for their role, we call them the oxidizing agent. But it's actually the thing being reduced. See, it's the opposite? That's what I'm talking about. Kind of confusing. I get it. And then here's the opposite of that. The reducing agent is the element that's being oxidized. It's responsible for losing the electrons gained by the element being reduced. So, to give them credit for their role, we call them the reducing agent. I think we need to do some practice so we can see what is going on here. So let's go ahead and do this, and I'm going to start with what I kind of expect you guys to do. First things first, let's label up the charges across the top. So lone elements are 0. Let's start there. Then Cl is a -1 if it's a negative, and there's 2 of them, so the overall charge is -2. So therefore, zinc must be a +2. Okay? Cl is a -1 times 2 is a -2, therefore this must be a +2. Now, this guy is a special thing, and I don't think that we put this in the vocab. We probably should have. This is what we call a spectator ion. He's just hanging out watching. He doesn't change. So when he doesn't change, we just call him a spectator. We cool with that? Okay, so I have MgO becomes Mg plus 2, and he must be losing electrons. How many did he lose? 2 electrons. And then Cn plus 2 plus 2 electrons becomes Zn0. And notice I knew the Zn0 had to go on this side if I had Zn plus 2 on that side. So I'm setting you up at the beginning. Okay, so the oxidation half reaction, if MgO is being oxidized, he is also the reducing agent. And if Zn plus 2 is being reduced, then he is also the oxidizing agent. He's the opposite. Okay, good. Good. Notice the agents have to be reactants, just like the thing that's being oxidized and reduced has to be reactants. They are oxidized or reduced on the other side. Okay, so let's not get the vocab wrong on that, the terminology. So again, I'm going to go ahead and label up my lone elements as 0 first. And then I'm going to start backwards, say, oh, this is a -1, so there must be a +1. And this is a -1, so this must be a +1. And I'm saying Hg0 goes to Hg plus 1. And then how many electrons from 0 to 1? Well, that's 1 electron. And then Ag plus 1 goes to Ag0. Whoops. Goes to Ag0. And how does it do that? Oh, because he gained 1 electron. And then HgO, if that's where the oxidation is happening, he must also be the reducing agent. It's the thing that's actually being oxidized. And the oxidizing agent, Ag plus 1. I would prefer if you talk your way through that every time, because do you think I might switch those things on the test just to see if you're paying attention? Maybe. All right, here we go. Ooh, I see polyatomics. Milks, why'd you do this? Same thing goes through our heads. First things first, zeros on our lone elements. Then I know NO3 is a -1, so Ag is a +1. I know NO3 is a -1, but there's 2 of them, so this has got to be a +2. So here's where we're going to come through with an issue. Cu0 becomes Cu plus 2. And 0 to 2 is 2 electrons. Okay, good. And then I've got Ag plus 1 goes to Ag0. Well, 1 to 0 is 1 electron. I don't need to write the plus because it's already there. But my number of electrons does not match. So I need to make that work. So what I do is I multiply this whole thing by 2 and say 2 Ag plus 1s plus 2 electrons goes to 2 Ag0s. And then those 2's going to come up here. So the 2 has to go here. And the 2 has to go here. And then, oh, look, I'm balanced because, see, it wasn't balanced with the NO3s. So there you go. So this is how we can balance using charge. Conservation of mass we did. Now we have conservation of charge. Okay, and those are very testable things. I didn't actually say it specifically now, did I? The reducing agent is the thing that's being oxidized, so that's Cu0. And the oxidizing agent is the thing that's being reduced, so that is Ag plus 1. Okay, and I think that's about it. You got some practice to do on your own. Try this out. I'll give you some more instruction in class, direct instruction about how this works, and hopefully you will figure this out because, again, this is the nuts and bolts of the entire unit. Best of luck.